Hello everyone and welcome to the AP Calculus AB/Calculus 1 summer course. Today is lesson 6, other types of derivatives. What this basically means is we're going to be covering exponential functions, we're going to be talking about logarithms, and we're going to be talking about absolute value/piecewise functions, which maybe you've heard of. I think we covered it earlier in the year or summer. But, and I forgot one more thing. We will also be covering arc trig or inverse trig. Now, in my opinion, these are some of the weirder derivatives out there. You might see them. You probably won't see them if you're taking a business calculus course in college. But if you're taking anything engineering-based or like a heavy math or physics kind of major, you're definitely going to be seeing these derivatives at some point. And also we get to talk about today my favorite number, which is the number E, named after my favorite mathematician, Leonard Euler. And today we're going to be talking about why the number E, and maybe you've heard of it, I assume you've heard of it at this point, the number E. The number E is a special number. It's equal to 2.718, and the decimal goes on forever just like pi. But the reason why it's special is because it's the only number in math, in calculus specifically, whose derivative is itself. In other words, if you have f of x equals e to the x, then the derivative f prime of x is the exact same thing, e to the x. There is no other function in the world with this property except the number e and its exponent. So in case you're wondering what does that mean, let me just show you an example. Let's say I just draw a graph of e to the x, which looks something like this. That's good enough. And let's just look at the coordinate point here. This is when x equals 1, the y value for e to the x. I mean, if you have y equals e to the x and you're plugging in x is 1, then y equals e to the first power, which is just e. So in other words, 2.718, we'll just say that for now. There's your coordinate point. Now, if you want to know what the slope is at that point, the slope is exactly the same thing. The slope is going to be 2.718. And if you want to know what the second derivative is, which we talked about acceleration before, that's also going to be 2.718. Every derivative after that is the exact same thing, and only e has that special property, which is why it's the most important number in calculus. Okay, so with that being said, all you need to really know is that if you have f of x equals e to the x, the derivative is the same thing. Another thing I want to tell you, we have another late entry. Another thing I want to tell you is that if you have a weird function, like let's say you have f of x equals e to the u power, where u can be anything. And I don't mean that as a motivational statement, u can be anything, but I'm saying u can be 6x, u can be 5x minus 4, u can be sine x. Whatever you have in that exponent, the derivative is equal to u prime times e to the u. After we talk about e to the x, the next function is a to the x, and a to the x is the exact same thing, except a can be any number. So as an example, if you have f of x equals 2 to the x power, then this derivative is almost the same thing. It's 2 to the x times the natural log of 2. Now, by the way, that technically, that natural log is there for e to the x as well, but the reason why it doesn't matter is because if you have f of x equals e to the x and you want the derivative, it would be e to the x times the natural log of e, and you plug in natural log of e in your calculator, and you'll just get 1, so you don't actually need it. But this is the generic formula in case you have anything as a base 2, base 5, base pi, base anything except e. You multiply by the natural log. One more thing I do want to say when it comes to exponents, a lot of people, basically they just mix it up with the power rule. They'll say if you have e to the x, well then it's x e to the x minus 1. That's the power rule. That is horribly wrong. Don't do that. Derivative is just e to the x. Okay, now we're going to talk about the logarithm. So the logarithm has the derivative 1 over x, where x is greater than 0. Now, I don't really care if you remember or forget the x is greater than 0 part. Really doesn't matter that much, so I'm not going to make a big deal out of it. But what I am going to say is if you have the function f of x equals the natural log of x, then the derivative of that is just 1 over x. And if you have something like, let's say, f of x equals the natural log of u, or once again, u can be any function in math, then the answer f prime of x is going to be u prime divided by u. This is the formula. You should probably write it down and star it or whatever because it's important. And that's basically it for this page. And so now let's go on to the next page where we talk about log base a of x. So in other words, this is no longer the natural log. By the way, the reason why natural log is so special isn't that because it's log base e of x, and e is that special number we talked about before. So if you have anything other than, like let's say I have log base 2 of x, well then the answer, well actually that's the example right here, so let's just do it here. The answer for the derivative is f prime of x is equal to 1 over x times the natural log of a, which is 2 in this case. So you'll notice it's almost the same thing as 1 over x, except you just add that natural log of whatever in the denominator. And then can someone tell me what the derivative of 3 to the x will be, using the same logic from the last page? That's right, it will be 3 to the x times the natural log of 3. Because 3 to the x is the derivative of itself, and since 3 is not e, you have to add on a natural log of e at the end of that. Any questions so far? Okay. Next up, we're going to be talking about derivatives of piecewise functions. Now, piecewise functions, these are the things that have like the top part and the bottom part for the different portions of x. Even if you don't know how to graph them, that doesn't really matter. The derivative of these functions is actually really easy. All you got to do is take the derivative of the top and the bottom separately. Now, here's what it looks like. F prime of x equals, the top part is derivative of x squared is 2x, derivative of the bottom part, derivative of 5x is just 5. Really easy stuff here. Now, the only thing that's even remotely challenging with this is remembering to change the bounds. Here's what I mean. X is less than 1, that stays the same. X is greater than 1, you don't get the equal to. Why not? Because if you plug in 1 for x, you're not going to be differentiable. What does that mean? It means if I plug in 1 for x here, it's going to be 2 times 1, which is 2. And if I plug in 1 for 5, well, I can't plug in 1 for 5, it's just 5. Since 5 does not equal 2, it is not differentiable. And since it's not differentiable, oh, and by the way, what does differentiable mean? Differentiable is a fancy word saying that the derivative does not exist. Derivative doesn't exist. And specifically, we're talking about at x equals 1. We're talking about x equals 1 here. And so since the derivative does not exist at 1, you cannot put the equal sign. See how that one has the equal sign right there? You do not get an equal sign for the derivative. Now, by the way, another reason why it doesn't get the equal sign is because I said it's not differentiable, which means derivative doesn't exist at 1. I could even say it's not continuous. Why not? Because if I plug in 1 into the original equation, it's 1 squared, which is 1, and 5 times 1 is 5, you're not even continuous, let alone differentiable. So it's like you got hit with a double whammy. In other words, even if, let's say, both these numbers here for the derivative were 5, it doesn't matter because it's not continuous either. And so for 2 reasons, you're not going to get the equal sign on this one. Any questions on what I'm saying there? It's funny because I'm making it sound like it's a big deal. If you forget that, it's like minus half a point, not the end of the world. But what's most important is just take the derivative of the top and the bottom. I will say, especially on the AP exam, there are questions where it's like, is this function differentiable at this point? And like that's the entire question. And if you get that question wrong, I mean, there's no partial credit on multiple choice on the AP exam. So you'll just like get the whole question wrong. So it's important for that part where you remember what differentiable means, derivative doesn't exist at whatever point. But besides that, it's not that big a deal. So we're going to move on. Next up, derivatives of absolute value functions. This is probably the hardest thing that we're going to be talking about today. And it's because that absolute value functions do have a derivative, but in order to make it a derivative, you need to turn it into a piecewise function. Here's what this entire page is basically saying. If you have the function f of x equals the absolute value of x plus 3, then the first thing you're going to do is you are going to set it equal to 0. You're going to say x plus 3 equals 0. And then you're going to solve for x. You get x equals minus 3. The next thing you do is, before you actually make it into this piecewise function here, I'm honestly going to cross out this step because it's just confusing to me. I'm going to basically make a number line. And on that number line, I put negative 3. And what I'm going to basically plug in points into is I'm going to plug in points into the function x plus 3. Now let's plug in something like negative 4, something to the left of negative 3, something in this region right here. If I plug in negative 4, I'm going to get negative 1. It's negative 4 plus 3. It's negative 1. And so I don't care about the negative 1. I care about the fact that it's negative, which means that that entire portion of the graph is negative. If I plug in a number like 0, 0 plus 3 is 3, positive, that entire region of the graph is positive. Now what you need to realize is what an absolute value function is. Most people think absolute value just means if you have a negative number, make it positive. Like if I have absolute value of negative 2, you make it positive 2. And of course you'd be correct because that's what an absolute value is. But in math, how do you make that happen? The answer is, what an absolute value function does is it adds an extra negative sign if you have a negative number, making it positive. That's really what an absolute value function is doing. It's not making it positive. What it's really doing is, if it's negative, you force it to be positive by adding a second negative. Now, what's the big deal? What's the difference? It's because when I'm making my piecewise function, back on this page, look at this step right here. F of x equals x plus 3, no absolute value signs when x is greater than negative 3. That's this portion of the graph right here where it's already positive. Then look at what they do for less than negative 3. For less than negative 3, it's the exact same function. Ignore the dog. It's the exact same function, except there's a negative sign in front, and that makes the result positive. Isn't that so cool? And now the only thing you might be wondering now is, why does this one get the equal sign and the other one doesn't? Honestly, it doesn't matter. If you want to write x is greater than or equal to negative 3 and then the other one's less than negative 3, that doesn't matter. I don't care. Neither would your teacher. It's the exact same thing. But one of them has to get an equal sign. Any questions? Oh, and if you want to take the actual derivative, now it's the derivative of x plus 3, which is 1 plus 0 for the derivative, so just 1. And then the derivative of negative x plus 3, you can distribute the negative sign, negative x minus 3. And the derivative of negative x minus 3 is negative 1. There's our derivative for this absolute value function. So again, what do we do if we have an absolute value function? Let's just recap. We set it equal to 0, solved, plugged it on a number line, and found out where the function's positive and negative. And where it's negative, you need an extra negative sign to counteract it. Then you took the derivative of the top and the bottom, just like we would for any piecewise function. Any questions? Okay. So with that, we move on to an example. We have the absolute value of negative 2x minus 1. So again, I'm going to do exactly what I just said. I'm going to say negative 2x minus 1 equals 0. Solve for x. So negative 2x equals positive 1. Looks like x equals negative 1/2 this time. Then I'm going to plug it on a number line. I've got negative 1/2 here. Now I need to plug in a number less than negative 1/2. There's many good choices here. Negative 1 will work. Negative 5 will work. Negative 1 million will work. I'll choose negative 1. And remember, I'm plugging it into my original negative 2x minus 1 to see if I get a positive or a negative. So I plug in negative 1. I get negative 2 times negative 1 minus 1. That gives me positive 1. So it's actually positive in that region. And then if I plug in a number greater than negative 1/2, again, a lot of good choices here. You got 0, 1, 2. Even negative 0.25 would work if you're feeling adventurous. But I'm just going to plug in 0. So negative 2 times 0 minus 1, that's negative 1. All I care about is the negative. And there's my number line. And now from this number line, I'm going to construct my piecewise function. If you want, you can either start with the function itself, or you can start with the x is less than negative 1/2 and x is greater than or equal to negative 1/2. I don't care what you start with. I'll start with that because I think it's easier. But the function, since it's positive over here, I don't change it. Don't change it for the positive. Negative 2x minus 1, just get rid of the absolute value sign. You don't need it anymore. And then for the other one, you just slip a negative sign out in front like this. And if you want, you can distribute that negative to both terms, and I'll do that. You get now positive 2x plus 1 when you distribute the negative sign. Any questions on that so far? We're not done yet, but any questions so far? Okay, good. Now the derivative. The derivative, it's simple. You just take the derivative of the top and the bottom. Derivative of negative 2x minus 1 is negative 2. Derivative of 2x plus 1 is positive 2. Notice that when we write the derivative, it doesn't get an equal sign this time. Why not? Because negative 2 does not equal 2. Therefore, the derivative does not exist at negative 1/2. Any questions? Okay. Hopefully that's easy. That's the hardest, maybe not easy. Hopefully it's not too difficult because that's the hardest part of today's lesson. And then the very last thing we're going to do is the arc trig derivatives. Honestly, I'm just going to tell you to memorize these. And basically, I know you're not going to have time to memorize these in the short time we have together. So you can just look at these for a second. Arc sine is 1 over square root of 1 minus x squared. Cosine is the exact same thing, but the negative version of it. Tangent looks like 1 over 1 plus x squared. I'm going to skip to cotangent because it's just negative tangent. And then secant's really interesting. Secant and cosecant have this like absolute value sign in the denominator. Do not turn that into a piecewise function. That would just, don't do that. Just keep it like this, okay? This is what they're expecting on the AP exam or even in your classes next year. Okay, any questions on that? And by the way, for this arc trig stuff, there's a lot of candidates for the least important thing in all of Calculus 1. This might take the cake for the least important thing in Calculus 1, which is amazing because it even shows up in my summer course, which it probably shouldn't, but whatever. I'll probably change it next year. Oh, and by the way, if you remember from week 3 or week 4, we were talking about the rules of derivatives. Well, now you can basically take the derivative of any function you can think of. Like even something stupid and crazy like e to the natural log of x power times the arc secant of the square root of x. You can take the derivative of this, and this is actually not that bad because it's a product rule here. We know the derivative of, well actually this is funny because e and natural log cancel, it's just x, times arc secant of root x. Well, that's going to be that same arcsecant formula I just showed you on the last page, which you have in front of you. And it's going to be a product rule. We could take the derivative, blah, blah, blah. I'm not going to spend time on it because it would take too long. But the point I want to make is you can now, with your arsenal of things on these 2 pages right here, theoretically, you can take the derivative of just about any function you can think of. The only one that I would say you can't take the derivative of yet, and this is a fun one, if you'd call it fun, is the function y equals x to the x power. This is probably the only family of functions you can't take the derivative of yet. Believe me, it is harder than it looks, and you'll probably cover that in the school year next year. But I'm going to ignore that because that's beyond the scope of this summer. Anyways, we're going to go into some practice problems now, and we'll probably end early because there's not actually that much more stuff to do today because this is it. I'll tell you, next week will be fun. Next week we're covering, it's called the first derivative test. It's probably, I say this a lot, I've realized, but first derivative test is probably my favorite thing in the summer course. And it's because it's the biggest application to real life, and that would be finding maximums and minimums. We're going to be finding maximums and minimums on a graph next week. Probably the most exciting thing. Also, it's something that I've been doing a lot with. I meet with a lot of college students over the summer. They're taking like a real college calculus class. They're doing the same stuff, that first derivative test that we're going to be covering next week. And another kid that I met with literally today, we are literally doing derivatives of these absolute value functions. So I can tell you it shows up. And he goes to Rutgers. He's a mechanical engineering major at Rutgers University. So I can promise you it's at least aligned with that. So anyways, we're going to take the derivative of these functions. The first one here, 3 to the x power plus 3x. Remember, if we want to take the derivative of 3 to the x, the derivative is 3 to the x, it's the same thing, times the natural log of 3. And we do that because 3 is not our favorite number e, or else that wouldn't be there. And then plus the derivative of 3x. Maybe you're overthinking it. The derivative of 3x is just 3. There's our answer. Short, sweet, and to the point. Next one, we have f of x equals 5 log base 7 of x. Remember what we said before. If you have log base a of x, that's going to turn into 1 over x natural log of a. So in this case, a is 7, and 5, I mean, that 5 is a coefficient. Just pull the coefficient out in front. So when I take this derivative, it's 5 out in front times 1 over x natural log of 7. And if you want to make this look nicer, you can just put the 5 in the numerator. That's fine. And you'll get this, and this is a beautiful final answer for the derivative. Any questions on those first two? Okay, now for number 3. Remember, for absolute value functions, first thing I'm doing, I'm setting this equal to 0. 5x plus 4 equals 0. Subtract 4 from each side. 5x equals negative 4. Looks like we're going to get x equals negative 4/5. Okay. So now I'm going to make my number line. And on my number line is negative 4/5. And then I'm plugging into the function 5x plus 4 because I want to see where it's positive and negative. If I plug in 0, for instance, I'm getting a positive number. 5 times 0 plus 4 is positive. So positive when x is greater than negative 4/5. And then when x is less than negative 4/5, I need to plug in a number like negative 1 will work. So 5 times negative 1 plus 4, that's negative 1. So that's negative in that region. And now I got to rewrite this function as a piecewise function. That's okay, not too bad. So in the top, where x is less than negative 4/5, that I see is negative. So I got to put an extra negative out in front. So negative 5x plus 4 in parentheses. And then when x is greater than or equal to negative 4/5, I'm going to say just normal, good old-fashioned 5x plus 4. And now when I take the derivative of this, I have to take the derivative of the top and the bottom. So f prime of x equals the top. Derivative, I mean, if I distribute that negative, it's negative 5x minus 4. And the derivative of negative 5x minus 4, that's just going to be negative 5. It's just a constant rule. And then the derivative of 5x plus 4 is 5. And then that's when x is less than negative 4/5. And this is when x is greater than negative 4/5. Remember, no equal sign, right? Because negative 5 clearly does not equal 5. That means the derivative does not exist at that x value. Any questions on number 3? Hopefully it's starting to get easier now, each time. And now we're on to number 4. Number 4, we have a piecewise function. By the way, piecewise functions aren't that bad because we get to save a step. What's that step? I mean, number 3 was way harder because you have to set it equal to 0. You got to put in the number line, all that stuff. I'm saying you don't have to do that here. All you have to do is just take the derivative of the top and the bottom. So the derivative of the top is 1/4 times x squared. That's going to be 1/4 times the power rule times 2 times x to the first power. I can reduce that if I want. It's just going to be 1/2 x. Literally just 1/2 x. And then that's when x is less than 2. And then for natural log of x, what's the derivative of natural log of x? Does anyone remember from the audience? It's going to be 1 over x. Just 1 over x. And that's when x is greater than 2. Now, once again, I'm not saying equal to for 2 reasons. Because if I plug in 2 here, I'm not going to get the same thing. 1/2 times 2 is 1. 1 over 2 is 1/2. Not the same thing. And by the way, even if they were the same thing, the original function was not continuous. If I plug in 2 right there, I get 1. If I plug in 2 right there into natural log of x, then I get natural log of 2, which is obviously not 1. So I don't get the equal sign on the derivative. And there we go. There's my derivative. Not too bad. Any questions on number 4? Okay, then let's continue. Number 5 is an interesting one because it's the arcsine function. So first, I'm just going to save you the trouble so you don't have to look back at your notes. If you have the arcsine of x, then the derivative of that is 1 over the square root of 1 minus x squared. Now the problem is we don't have x. We have 2x cubed. So what am I going to do? So basically, if you have some function u, where again, u can be anything, then the derivative is numerator, u prime, denominator, square root of 1 minus u squared. And in this case, u is 2x cubed, and u prime is the derivative of 2x cubed, which is 6x squared. So now I just need to plug it in this formula right here. And it's going to be f prime of x equals u prime, which is 6x squared, divided by the square root of 1 minus the quantity 2x cubed, and that whole thing is squared. You can leave it like this if you want, but I'll reduce it just because I'm curious and because I can. So it's going to be 1 minus, if I square 2x cubed, remember I have to square both the 2 and the x cubed, so it's going to be 4x to the 6th power. And that's our final answer. This really can't be reduced anymore. Any questions on that one?
I just have a quick question. So because the arcsine derivative is inclusive of any value u,
yes,
there's no chain rule on the 2x cubed.
Yeah, that's a good question. The answer is we actually took care of the chain rule when we put it in the numerator with that u prime.
Cool, thank you.
Yep, so in other words, my formula that I invented and copyright and patented, and I will sue you if you steal it, but okay. I will let you use it because I have it on video. I'll let you use it. Basically, what I'm saying is, yeah, with my formula, it already accounts for the chain rule. The same, by the way.
Yeah.
The same is true for natural log of x. Remember when I said natural log of u becomes u prime over u? Really, what I'm doing two things. I'm doing 1 over u times the derivative u prime. But, who writes it like this? I mean, I'll admit my college students do, but that's because they're my college students and they're dumber than my high school students. But it's u prime over u. It's the same thing.
Oh, okay, makes sense. Yeah, so we're just multiplying, so it goes to the numerator.
Yes, exactly. Any other questions? Okay, excellent. Now for number 6, we have log base 4 of x squared. Again, it's the same idea. If I actually basically just said it. If I have natural log of u, it's going to become u prime over u. But I got to be careful because I don't have natural log of u. I have log base a of u, which will become, does anyone remember the formula or want to take a shot at this formula?
It's 1 over x.
Oh, I don't mean the final answer. I just mean in terms of u right now.
Oh, it's like 1 over u to the something log
a. Natural log a. And it's not it's not u in the, it's not 1 in the numerator anymore. It's u prime now because that accounts for the chain rule. So then here I'm saying u is x squared, u prime is 2x, and a is 4. And with that, I just plug into this nice formula here. So then we're going to get f prime of x equals numerator 2x, denominator x squared times the natural log of 4. And there we go. Oh, and by the way, you can reduce this because one of the x's cancel. So you could say another answer is 2 over x natural log of 4. And I would accept that as well. Any questions? Okay. Now, one thing I do want to mention that in the homework solutions, I probably have a little extra x is greater than 0 here as part of the solution. That's because technically x needs to be greater than 0, and you need to include that domain in the answer. There's a good reason why. I don't really feel like sharing because it's not that important right now. This is the last thing you need to worry about right now. So I'm just going to tell you it's there, but don't worry about it. Now, number 7. Number 7 is honestly the hardest problem of the night because it is a chain rule with a product rule inside, which is really hard. So I'm definitely going to help us with this one First thing I'm going to do is I'm going to rewrite this as x squared times secant x raised to the 1/2 power. Remember, whenever I have a square root in this class, I'm really writing exponent 1/2 power. And then, if I want to take this derivative, then I'm going to say derivative for the chain rule. If you remember chain rule, you got to do derivative of the outside first. So f prime of x equals, pull that 1/2 down. Don't take the derivative of the inside yet. Just write it again, x squared secant x. And then that's raised to the 1/2 minus 1 power, that's negative 1/2 power. And now we're going to multiply it by the derivative of the inside. So this one's pretty challenging. I'm going to write it on a separate sheet because I ran out of room. But I'm going to say u is x squared and v is secant x, arcsecant of x. Is that what I wrote here? I forgot to write the... That's funny. Number 7 is... I'm positive number 7 was supposed to be arcsecant. There is no way I don't have that. So that's supposed to be arcsecant, that's supposed to be arcsecant, that's supposed to be arcsecant. That's a typo. Anyways, back here. V is arcsecant of x, u prime is 2x, and v prime is the derivative of arcsecant, which is 1 over the absolute value of x times the square root of x squared minus 1. And remember what product rule says. I know it's been a while, but product rule says the derivative is going to be u times v prime plus u prime times v. Think of it like cross multiplying. That's essentially what we're doing. So then the derivative is going to be, put it all together, it's going to be x squared times 1 over absolute value of x times the square root of x squared minus 1, and then plus u prime times v, 2x times the arcsecant of x. And you can probably reduce this. I am not going to ask you to reduce this. This is way too difficult. And so this is fine as our final answer. Any questions? Okay, good. Number 8, it looks like we have a quotient rule. Once again, I have tangent x over x squared plus 5. It's supposed to be arctangent. So number 8, we have arctangent of x divided by x squared plus 5. This is a quotient rule. So it's just going to be u equals arctangent x. V is x squared plus 5. U prime is the arctangent derivative, so 1 over 1 plus x squared. Technically, you can write 1 over x squared plus 1 if you really want to. That's the same thing. And then v prime is just 2x. And now when I take these derivatives and multiply, well, remember the formula. It's v times u prime minus u times v prime over v squared. That's what quotient rule says. So then following my formula, it's parentheses x squared plus 5, close parentheses, times u prime, which is 1 over 1 plus x squared, minus u, which is arctangent x, times v prime, which is just 2x. And then all of that is over v squared, which is quantity x squared plus 5 squared. And again, we don't have to reduce this. This is fine. They will accept this. Any questions on that one? And now we're on to the last problem of tonight. Number 9, e to the x times the arc cosecant of x. Can someone tell me the strategy I'm going to be using to solve this one?
Product rule?
Yes, it's product rule. So then that means u equals e to the x, and v is the arc cosecant of x. So who knows what u prime will be from the audience?
E to the x.
Thank you. And who knows what v prime will be? That one you can just look up. Negative 1 over the absolute value of x times the square root of x squared minus 1. Yeah, that's a fun one. And by the way, I've gone over practice AP exam tests before. Typically, you're not going to see more than one question on the entire exam that has this stuff on it. Anyways, since it's product rule, you basically cross multiply. So the final answer is u times v prime, which is e to the x times negative 1 over absolute value of x times the square root of x squared minus 1, close parenthesis, and then plus u prime times v, e to the x times the arc cosecant of x. And we're done. There's our derivative. Any questions on number 9? Okay, then that's going to do it for today. I know it was a short lesson. I apologize. But the good news is that now you have more time to do whatever you do on a Monday night. For me, it's tutor, in case you're curious. Anyways, that's it for us today. Thank you all for watching. I'll be posting the homework after this. Have a great rest of your night, and bye-bye.